DePIN starts in the physical world, but blockchains cannot process raw device telemetry at scale. Instead, data is collected and processed off-chain, verified through oracles and attestations, and then only trusted results reach smart contracts, incentives, and customers. So far, we've covered DePIN fundamentals, incentive design, and the technical stack, devices, edge infrastructure, and proof mechanisms. Now we connect those pieces by looking at how raw device outputs become trusted data for rewards, customers, analytics, and settlement. Data is the nervous system of a DePIN network. Devices sense real-world activity: bandwidth delivered, storage available, energy produced, compute used, or location verified. That information flows into verification and reward logic, turning physical service into payments. Customers rely on it too for SLAs, dashboards, billing, and operational decisions. If the data is wrong or manipulated, incentives break, prices distort, trust falls, and disputes follow. Telemetry is the evidence layer for DePIN. A wireless hotspot may report coverage, signal strength, location, uptime, and throughput. Compute or storage nodes report availability, latency, completed work, resource usage, and proof results. Sensors report readings like temperature, movement, energy use, or geospatial observations. Device context matters as well. Firmware, cryptographic identity, and operator status help determine whether data is trustworthy enough for rewards, routing, or network decisions. The data pipeline acts like a trust factory. Devices produce messy signals. Ingestion captures them from gateways, apps, SDKs, or edge nodes. Validation removes duplicates, bad records, outliers, and suspicious activity. Normalization turns different device formats into one consistent schema. Enrichment adds context, and storage makes the result queryable. From there, analytics, dashboards, APIs, reward logic, and governance reports can all use the same verified data product. Reliable ingestion is the shock absorber between field devices and downstream systems. Data may arrive through MQTT, HTTP, WebSockets, gateways, SDKs, or edge agents. First, each device proves its identity. Events are then received, timestamped, and placed into queues or streams, so bursts do not overwhelm processing. If networks fail, buffering and retries preserve the data. Acknowledgements close the loop by confirming what was captured and what must be resent. Before telemetry can drive rewards or reporting, it has to pass a quality gate. Normalization makes records comparable by aligning time, location, units, identifiers, and schemas. Filtering removes duplicates, corrupted payloads, impossible readings, and spam patterns. Enrichment adds context, such as region, reputation, or account mapping. Finally, quality scoring separates trusted records from uncertain ones, so downstream systems reward real contribution rather than raw volume. Once telemetry is cleaned, the next question is how it will be used. Fast operational checks need hot, time series storage for uptime, throughput, energy, and sensor trends. Deeper analysis belongs in a data lake or warehouse, where teams can train models, investigate fraud, and build reports. Indexing by device, region, time, operator, and customer keeps queries practical. Retention policies decide what stays hot, what moves to archive, and what can expire. DePIN becomes a product when infrastructure data turns into something people can trust and use. Operators need dashboards for node health, uptime, earnings, alerts, and performance trends. Customers need APIs for verified coverage, capacity, usage, sensor readings, billing, or delivery status. The challenge is not just displaying data. It is guaranteeing freshness, accuracy, access control, and rate limits, so analytics, invoices, SLAs, and protocol verification all tell the same story. To connect physical events with smart contract decisions, DePIN systems need a trusted path on-chain. Oracles collect external inputs, such as sensor readings, location proofs, or market data, and deliver them in a form contracts can use. Attestations add accountability by having someone sign a claim about what was observed. Because real-world data is messy, the network filters, verifies, and aggregates before publishing. The goal is not maximum data on-chain. It is trustworthy results that can trigger rewards, settlements, or governance. Oracle design is a trade-off, not a universal choice. Trusted oracles are fast and cheap, but credibility depends on one authority. Decentralized Oracle networks add redundancy and attack resistance, but they also increase cost and coordination. Validator reporting aligns data claims with staked incentives and penalties. In DePIN, hybrid models are common. Centralized systems handle operations, while decentralized checks, disputes, or slashing protect the network when reports are wrong. Attestations create a chain of signed claims. A device signs an event with its key. A gateway can add context, a validator can check rules, and an oracle can bundle the result for a smart contract to verify. This improves provenance. We know who claimed what and whether the claim changed. But signatures do not prove the physical world was honest. Spoofed sensors, tampered hardware, collusion, and compromised devices still require separate defenses. DePIN networks generate too much fast-moving data for blockchains to process directly. Sensor readings, routing decisions, fraud checks, simulations, and machine learning need cheaper, faster off-chain systems. The chain should act more like a settlement court, recording commitments, resolving disputes, governing rules, transferring tokens, and finalizing rewards. The hard part is not moving computation off-chain. It is bringing results back with enough proof, auditability, and accountability that participants can still trust them. In practice, DePIN design is rarely fully on-chain or fully off-chain. High-frequency sensor data usually stays close to the device or edge, where it is cheaper and faster to process. The chain is used for what needs public verification: hashes, proofs, summaries, rewards, and settlement. More transparency can build trust, but it can also raise fees, expose sensitive data, and slow decisions. Good architecture chooses the minimum on-chain footprint that still protects users and keeps operators accountable. DePIN operations depend on three connected layers: data pipelines that clean and organize telemetry, oracles and attestations that make off-chain reality usable on-chain, and off-chain compute that provides scale and responsiveness. Next, we'll apply a security lens to protect these systems, improve resilience, and manage operational risk.